directly proportional to the velocity, or x naught. That's the velocity. So if you remove that proportionality, then that damping force F is equal to C
Use the lighter
x naught. Right?
1.2016.
Seen that before in the first lesson.
There's two. Wait, I see.
So this C will be our damping
Oh, really? Nice.
coefficient.
No, this is not. No, there's two.
And if
You
it's
see?
linear coefficient, that means the units is newtons seconds per meter. For rotating system, and later on there'll be an example to show you a rotary system. The units for that would be newtons meter seconds per radian. So this for a translational system, the units for damping coefficient. This is for rotating system, the damping units will be given like this. Okay. So today we're going to talk about damped system. So it's not undamped over here. This will be damped. Right. So I'm going to sketch the damper. If I add a damper in here, it's going to look something like that.
He copied and used a bit.
It's going to look something like that. So if I have it over here, attach it to a mass, then the mass is going to pull it down a little. In that way. So this part here is going to get pulled down, right, the lower part. So maybe I noticed that some of you don't really know how a damper works. So this part here is one piece. This part here is another piece. Okay. So you can move this thing upward. So then it slides along the cylinder and it becomes better. That's how the damper works. So what I've sketched over here is for the static condition. If you look at the disturbed condition, then you're going to pull down that damper together with a spring. So probably it's going to look something. Okay.
I need backup also.
Right. So what I've sketched is that this kind of space that's in there will be increasing. It's not really sketched to scale, but you get the essence of it as you have the dynamics or the disturbed condition, and the damper will be pulled down. The damping coefficient, C, will be the same for all these various cases. And that amount that has been displayed, we were saying that is equal to x naught. It is quite the dynamic deflection, but it has a maximum value as you pull it down and you release it and it will oscillate. So let's have a look at the free body diagram and the free body diagram. So in order to sketch a free body diagram, we need to cut these two ends. And if we were to do that, we saw that for the spring, it's going to look like that because the spring will be under tension. So if it's under tension, then I sketch that way to show that the spring is under tension. You pull it. And there will be an equal and opposite force in that way. Okay. If I were to cut the damper, this is what's going to happen. So damper will be cut. So for a static condition, so I'm going to write down For the static condition, there is no force. I'm going to underline that. Acting on the damper. So that means these forces over here, F, due to the damping, F will be equal to 0 for all of them. That's for the static condition. Why is that so? Because the damper, if you don't move it, then it doesn't provide any damping force. That's unlike spring. Spring, you gotta compress it and stay there, you still get that spring force. For damper, you gotta compress it and stay there, then you wouldn't find there's any more force. It's only when you are pressing, in the process of pressing. So for the disturbed condition, this is what you're gonna have. Because it's being disturbed, that means being moved. So if I were to break that link in order to find a free body diagram, then I'm gonna get the respective forces due to the damping. So in this case, the damper would be under tension as well. So equal and opposite force. And the force that's over there, the damping force F, will be equal to C x dot. That's the damping force. The spring force, you had seen before, that was in the last week. In the last week, that spring force, in this case, F, is equal to K delta static plus X. Right, that's your spring force. So we're gonna sum them together today. So there'll be this four damping forces. So in order to help you to visualize, what I have is the small little model.
So what I have over here. So what I have over here is this Lego pieces, and this one has got a spring that's embedded in it. So if I were to press, I can feel. You can see my finger over here. Right, there's a constant force acting on it on my finger, and if I release, it will come back. So I bought two, and I took out the spring. So again, the spring, if you were to press on it, then you can see that there's forces that's acting on it, on my finger. Right? No matter at which stage of compression, there's always a force that's acting on it. But for the damper, it's a bit different. The damper, you're going to notice my finger over here. If I were to press on it, you can see that it moves, and then there's a force that's acting on it. And once I stop, there's no force that's acting on my finger. So what that means is that this is the case of static condition. When I stop, there's no force acting on it, and in order to experience this damping force, I need to have constant movement. That constant movement comes about because of the dynamic condition that we're talking about. It is. So please take note of this.
Please take note of these differences. So always remember, in static condition, there's no force from the damper, but there's force from the spring. In the disturbed condition, there's forces that's coming in both from the spring and the damper. So let's build up the equation of motion. Let's start with the static condition. So for the static condition, we'll sum up the forces Fx, and then that must be equal to 0. What kind of forces? We are interested in this area. Considering the mass, right? For the static condition. So sum up all the forces. What you have is mg, that's in our convention direction, so it's positive value. And that spring force F is equal to K delta. I'm going to stop writing that static ST subscript. So minus K delta equal to 0, right? The two forces. And that spring force is acting upward, so it's against our convention, so there's a minus sign. Let's consider for the other one, the dynamic condition. Also considering around the mass. So this is the one that we're interested in. And the force for that spring, F, is equal to K delta plus X. Right. So do the same thing, summing up the forces in the direction of X, and sum that because dynamic condition, so it's equal to mass times acceleration. So mg is in the direction of our convention, it's positive value, minus force that's due to the spring in the opposite direction, so minus k delta plus x. And there's another force, there's a spring force, so I'll use the red color. And that damping force is in the opposite direction, so minus c x dot. So equal to m x dot dot. So let's break out that bracket. mg minus k delta minus kx minus cx dot equal to m x dot dot. So this term over here, we can see from the static condition, this is equal to 0. So let me readjust a little bit. There's mx dot dot plus cx dot plus kx equal to 0.
Not bad. Try to answer.
So this equation over here,
Wow. Okay.
this is what we call the
Amused.
second order system. And it is the most basic form of a second order system
May
with
balik. Up down.
damping. So the case that we had last week, it was without a damper. So now what I've done is to add a damper. So that's why we have this term that's coming in. If you remember last week, there wasn't this term. Last week it was mx dot dot plus kx equal to 0. So now we have the damper, so that's that term. So we can simplify this by dividing it throughout by m. So I have c divided by m x dot plus k over m x equal to 0. I'm going to call this equation 1. Now we have seen before the undamped natural frequency. The undamped natural frequency, omega n, that's equal to square root k over m. That was seen last week. This week, I'm going to introduce to you a new term. Introducing damping ratio. So damping ratio is different from damping coefficient, so please do not mix up with these two. Damping coefficient, that's C, the C value. Damping ratio is this symbol over here. Right. This symbol is called zeta. Zeta or zeta, some of you learn in different ways. Note this symbol in your set of lecture notes. In printed form, it's kind of like written in that way. Zeta. So in handwritten form, I just write it in that way. Do not mix up this with another similar looking symbol. That one.
What is it? What's that?
What?
See?
That's called
That's a Chinese word.
psi. In Greek.
I see. In Chinese.
Please do not mix up psi with another Greek symbol that looks something like that. Right. You all write it better.
What is this? This is a sign.
This one is called
X. G.
it's pronounced Greek as Kai.
Then you need your son, right?
And this one probably you've seen before.
Thai something.
This one is Psi. Okay.
I like Thai.
So
Sounds like
we are not interested in this. We're interested in this one. That's zeta. So don't mix up with all your Greek symbols. So this damping ratio, for now, I'll introduce it in the following equation. C over 2 square root km. Right? Why is it in this form? Well, actually, if you do the units, if you put in all the units, you'll find that this is dimensionless. This damping ratio is dimensionless. It's going to tell us a property later on, right? So for now, this is definition. And I can re-express this with C as a subject. So C equal to 2 zeta square root km. Alright, later on I'll make use of this relationship. How this came about? Well, somebody was smart enough to put them together in this flowing way because they are dimensionless. Yeah? And why divide by 2? That's a certain purpose that you get to see later on. So this term over here we have seen before. For a second order system, this term C over M is actually equal to if I were to put this 2 zeta square root km for C and then divide it by M. So I need to simplify this term. Alright. And the way to simplify it is that I'll take this M over here, which has a power of 1. M is actually the same as writing it square root of M multiplied by square root of M. Right? You take the square root of M multiplied by square root of M, you get M. So I'm just going to break it down in that way. And this will be square root of Km. Now why I do that? That's because square root of Km is the same as square root of K, square root of M. So I can cancel this. So this will become 2 zeta square root K over M. This term square root K over M sounds good to us because isn't that the same as my undamped natural frequency omega n? So I'm going to replace it 2 zeta omega n.
Wow, magic.
So that's why this center term with the x dot, the coefficient that comes with the x dot, will be equal to 2 zeta omega n, and later on we'll make use of that. So equation 1 now becomes x dot dot plus 2 zeta omega n x dot plus this term over here we have seen in the natural oscillation or the free vibration. This term here is omega n squared x and then equal to 0. I'll call this equation 2. So equation 2 hence now will be our damped second order system. So you have seen this damped second order system. I wrote it over here. Right. So this is in terms of mass, damping coefficient, and spring constant. That can be expressed similarly in this following way. And this is one that you get to see more frequently. Yeah. So if I have this kind of second order differential equation, we always would like to find out what is the x t. Right? So that means we need to go about solving it. Is trying to find out what is the xt by using a few mathematical tools. Your lecture notes give you one format that is using the Euler's approach. I'll give you another approach that's using the Laplace transformation. So you can make a comparison. Right? So you get two. And in your exam, you can either use Laplace transformation or the Euler's method. And later on, we'll solve some questions that I'll use two methods. In today's class, we're going to pick up speed, so you wouldn't be going that slow. So if you find that it's hard to catch up, catch up. Don't just try to find it hard to catch up, just catch up. Okay?
It suddenly sounds so real, teacher. Why?
So let's have a look. Free vibration of them second order system. So remember, we're talking about a damped system, no longer about undamped system.
He know first aid.
So we need to have these few initial conditions. The initial conditions of when x, that is the displacement together with the spring and damper, at time equal to 0, that displacement is x naught. So you kind of cool it down with an x naught value before you release it. So that's your initial condition. And the other one, that is the velocity at time equal to 0. Just before you release it, that velocity is equal to 0. These are the two initial conditions. If I were to remind you, if I take Laplace, and this symbol over here, that looks like an L, that's the Laplace symbol. If I take Laplace of x dot dot, that's equal to s squared, capital X, f, minus s, xx times 0, and minus x naught, x dot, at time 0. So this term over here will be talking about our initial condition, and is equal to 0, so I can simplify it. It's s squared xs minus s, and this x at time equal to 0 will be x naught, substituting my initial conditions. If I were to take Laplace of x dot, then that will give me xs minus x at time 0 And how I got this is all coming from your Laplace table. So if you refer to your Laplace table, you'll be able to see these two lines. Together with initial conditions, again, this one can be simplified in the following example. Why do I take Laplace of this x dot dot and x dot? That's because I'm trying to solve this second order differential equation. So now, if I were to take Laplace transformation of this equation 2, taking Laplace transformation of that. So Laplace transformation of x dot dot now becomes this term that I just solved as s squared xs minus s naught plus 2 zeta omega n. I'm going to keep that. Laplace transformation of x dot, that will give me as xs minus x naught, and then the last term omega n squared xs equals 0. So I have a common factor that I can see, this one, this one, and this one. So I'll take it all out. xs, that will be s squared plus 2 zeta omega n x plus omega n squared. Right? So if you multiply n, you'll be able to see that. And bring the rest to the right hand side. So I'll have it simplified in the following way. S plus 2 zeta omega n. Right. So that's x naught for s. And then this x naught over here, 2 zeta omega n. So I simplify it in that way. So keeping xs as a subject, now I will have x naught, bring it to the front, and then s plus 2 zeta omega n over s squared plus 2 zeta omega n s plus omega n squared. I'll call this equation 3. So whenever we try to get what is this term xt, sometimes we call it the time response. If you want to try to do that, then after taking Laplace, you must be able to take inverse Laplace. But then we can't take an inverse Laplace on this form over here. Why so? That's because if I will show you your data sheet. Your data sheet, in order for you to take inverse Laplace, you must have this kind of form. Right? You must have the denominator part of this kind of form. So if you look at this form over here, it doesn't have that kind of format. So if it doesn't have that kind of format, that means we have to somehow make it into that format so that later on we can do it inverse Laplace. Why we need to do inverse Laplace? So that after inversing that Laplace, it will go back into the time domain. Now it's in the S domain. Right? So let's see how do we go about making that denominator in those formats. So to obtain xt, which is your time response, we need to factorize equation 3, factorize the denominator. And after we have factorized the denominator, then we take inverse Laplace transform. Yep. So let's focus on this denominator first. This is s squared plus 2 zeta omega n s plus omega n squared. If I were to take this and then do the factorization, right? Do you remember that there is that roots formula? Ax squared plus bx plus c equal to 0. Do you remember if you need to find x, there is this roots formula that is minus b plus minus square root. B squared minus 4 is divided by 2.
You'll get answer straight.
Do you remember this whole frame? Yeah, this whole frame. If you remember this old friend, that's good because today we're gonna party with this old friend.
What?
So if I apply this quadratic formula, right? This is called quadratic formula to this form. So that means my s will be equal to minus b
I know why I asked you
minus
to
2
download the
omega n
2016.
plus minus square root
Because that one you can do like what he's doing.
b squared. So
This is
this will
2016.
become 4 the square omega n squared minus 4a is equal
Because
to
when this one you
1
can section into a lot
and
of
c
things.
there will be omega
On top of the
squared
major section, right below there's at the set.
divided by 2a and a is equal to 1. So I can see that there's a common factor at the bottom here too. There's a 2 over here. And there's a square root 4 and 4. So what I'm going to do is take out that square root 4 outside. If I take out square root 4 outside, that will become 2. Because square root of 4 is equal to 2. So this, and this will cancel out. So what I'm left, there will be minus eta omega n plus minus, and there's a common factor as well, omega n squared. I'm going to take out omega n squared and square root. So that will give me omega n. So whatever that's left in the square root, that will be zeta squared minus 1.
Apple.
And denominator is over there.
Lousy.
So this is equal to, there's a common factor omega n, I'll take it out, minus zeta plus minus square root, zeta squared minus 1.
I think that 2016 is available on.
If you have a root that's in this way, when we put them together, it's going to be a little bit different. So what I mean is that, let's say for example, I'll give some numbers to this. Let's say maybe x squared plus x minus 6 equals 0. So if you use this quadratic formula, you'll find that x will be equal to minus 3 or x is equal to 2, right? After you factorize it. And in order for you to express it in an equation, so you take this x instead of minus 3 is plus 3, and then x instead of plus 2 is minus 2 equal to 0. So that's how you factorize it. Yep, in your earlier education. So the same thing. Now I have this kind of thing, that's kind of like my x term equal to this. So if I were to put them together, back together, my xs from equation 3, x naught is still going to be there. The numerator 2 plus 2 zeta omega n is going to be there. Right? If you refer back to your equation 3. Equation 3 is here, so I'm just rewriting this. But this part I have already factorized. Right? This part I factorized. So in order to put it into 2 brackets that multiplies each other, I'm going to make use of this term. So it's going to be s minus omega n minus zeta. And I'm going to use the first one first. That's plus square root zeta squared minus 1. And the other term over here is s minus omega n minus zeta. And instead of plus, over here is minus. And square root zeta squared minus 1. I'm going to call this equation star. Later on, I'll come back to it. So when I talk about equation star, you will know which one I'm referring to. So now that we have this form, this denominator in this form, so given that what we saw before, zeta is equal to c over 2 square root km, right? That was when I was introducing what is zeta. Could you now see that if c is greater than 2 square root km, then what will happen to zeta? It will be greater than 1. Yeah. So if c over here is greater than this denominator, that means your zeta here is greater than 1. I have another case. If c is equal to square root of km, then what happens to zeta? It will be equal to 1. Yeah. Another case, c that's lesser than 2 square root km. Then what happens to zeta? It will be less than 1, yes. So these three cases you have learned before in your earlier education. These two cases over here, where zeta is equal to 1 or greater than 1, these are called real numbers or real values. This one here will be your imaginary number. That is real number. So what I want to sum up is when zeta is greater or equal to 1, that means your omega n, this term over here, is a real number. And if zeta is less than 1, that means your roots is imaginary. So why do I mention this? That's because later on I'm going to depend on these two words. Is it real or is it imaginary? Because later on, the method used to factorize equation 3, right? Method used to factorize equation 3 depends on zeta. What is the value of zeta? So you've seen before, there's going to be 3 cases of zeta. So let's have a look. Case 1. When zeta is less than 1. This case 1, when zeta is less than 1, it has a name. We call it the underdamped system. Note, is not undamped system. Is underdamped, not undamped. Undamped was the case when there's no damping, and we discussed that last week. Today is with damping, and out of which damping, if zeta is less than 1, we call it an underdamped system. So what we're going to do next is to re-expressing equation 3 denominator. So if we re-express equation 3's denominator, I'm going to write it out here. That's the denominator, s squared plus 2 zeta omega n s plus omega n squared. If we were to re-express this, I know previously I've already done that factorization job, so later on I'll make use of that. But there's another way to factorize. And the way to factorize depends on if zeta is it greater than 1, lesser than 1, or equal to 1. So this is a case where zeta is less than 1. How do we factorize this? I'll factorize it, break it down into s squared plus 2 zeta omega n s. And I'll add a term to it. I'm going to copy down this plus omega n squared, right? So I'm going to add a term to it. This term is omega n squared zeta squared. If I were to do that, then I need to minus that same term, omega n squared zeta squared. Why do I add and minus this funny term? Later on, you'll be able to see why. So now I can split it up that way. Now, if I have a term that's in this round bracket in this way, this term is actually the same as s plus zeta omega n squared. They are the same. And this term over here, this omega n squared is a common factor. I can bring it down. So I have 1 minus zeta squared left. How this term came to this? Well, you can square it and you'll find that you get back to this term anyway. Right? That's the factorization. So I'll keep this term, s plus zeta omega n squared. And this term over here, I'm going to take the square out of it. That means omega n square root 1 minus zeta squared. I'll take that square out of it. So this term that's in the round bracket, this term over here, without the square, just the one in the round bracket, this is a new term that I call it omega d, where omega d is defined as damped natural frequency, or sometimes it's just damped frequency. Omega d is equal to omega n square root 1 minus zeta squared, that formula. So that can be simplified now as s plus 2 zeta omega n squared plus omega d squared. Right? This way. So this term about omega d is equal to omega n square root 1 minus zeta squared. If you're wondering, do I need to memorize that? Actually, you don't have to because I've inserted it into your data sheet. That's awesome. Where is it in the data sheet? Let's have a look. I'll come back to this slide. It's right at the front.
The s plus 2 for what? Brian, no need what? The s plus 2 zeta
You can find it
omega n,
over
right?
here.
No need what?
Omega d is equal to omega n 1 minus zeta squared.
Do you follow me?
So this is in
Okay, now you see the 2, now you see the 2.
this
How about
equation.
2?
So
S
3, after we have
plus
factorized it, now it
zeta
becomes
omega
the
n
following
square for what?
expression.
Why he plus 2?
X s
Tell him,
equal to x naught
Yeah, the 2 is extra.
s plus 2 zeta omega n.
Sir,
Sir, that s plus 2 zeta, actually the 2 is not needed, right? Yeah, there's a 2 there.
There shouldn't be a 2 here.
Okay. Wow.
Thank you.
Wow. Sharp. Wow. Wow.
So this denominator now will become s plus 2 zeta omega n squared plus omega d squared. This I call it equation 4. I need to factorize this further because why am I doing all this? Because I'm trying to get to a form so that I can do inverse Laplace. So far, I still could not. If you look at your Laplace table, there isn't a form that looks like this, but close enough. So what I need to do further is to factorize it more. This numerator, s plus 2 zeta omega n, I can break it down. S plus zeta omega n plus zeta omega n in the following way. Right? So that numerator, if you add them together, you get 2 zeta omega n. And this denominator would be the same on those two terms. S plus zeta omega n squared plus omega d squared. This term here, I'm going to keep it because it looks like now I could do an inverse Laplace for this. Later on I'll show you. So this term I'm going to keep. This term over here, I still could not do an inverse Laplace according to